what I hope to bring to the project is being a link between the experiments and the computations. So my work has been focused on infusion of measurements in simulations, people spoke to the difficulty of the measurements. Of course, ultimately, getting field measurements is the unparalleled in terms of realism, and we're trying to do controlled experiments, but at the end of the day, we have limitations in terms of where we can perform these measurements and getting as close as possible to the wall, but also the interpretation of the measurement. Whenever you measure, you're not actually measuring the quantity of interest, you measure something else and then you interpret it. If you measure the same quantity in two different ways, you get two different errors. So simulations, we try to claim that we have full field at high spatial temporal resolution. Obviously, this project challenges that claim. We're not going to be doing full spatial temporal resolution. We have the benefit of being able to do non-intrusive measurements anywhere we want in the computation, and that we can look at different terms in the equation. The difficulty we have are the modeling errors, and people spoke to the need to be able to validate our models that Carderock will be using in the future. And we often use computations in truncated domains, unlike the experiments that can simulate the entire geometry. So ultimately, where I come in is my view is that we should fuse the simulation and the experiment. And what we do is we put the measurements as constraints in our simulation. So if my simulation doesn't satisfy the measurement, I haven't converted within the computation that I satisfy the measurement. And by doing this, I ensure that my LES, for example, not only reproduces the measurements, but it's also reproducing trajectories of the flow in state space. So we're reproducing what is observed experimentally in our computation, not just the measurements, and gives us access beyond the measurements themselves. So these techniques, we've been applying them in 3 areas. One is to develop new classes of optimal LES models. If you give me integral quantities from a geometry, any statistical moments, I can optimize LES offline to make sure the LES for this class of problems reproduces the same statistics. So if Joe can give me detailed measurements within the boundary layer in this region, I can optimize my LES models offline to make sure that it is the best performance the models can give for this type of flow, this class of flow. The second place where we've been doing this infusion of measurements is then when you have spatial temporally resolved data to some extent. So these are not just statistical moments, this is, I'm getting PIV data. Then I can have what I call super resolution of the data. If the data is, for example, under-resolved in space or time, I can fill in the gaps. And if there is a blind spot in the data, so this is number 3, for example, if we make measurements and we cannot get all the way to the wall in some region, then we can fill that gap entirely by constraining the simulation to satisfy the available measurements. Just a comment about sensing. We often today talked about where to measure, where's the best place to measure. The interpretation of that changes when you think about those ideas of putting the measurement in the simulation. If you're interested in measuring the flow, we often want to know exactly where separation will happen and measure that region. But in this interpretation, you want to measure where, once you inject those measurements in the computation, you get the best estimate of the flow everywhere. Okay, so just to give you an example, I'm not going to show an example from 1, I'm just going to jump directly to 2. So super resolution. This is an example of a computation of wall-bounded turbulence. And imagine if these are the only measurements that we have. These measurements are 1/4000 the DNS resolution. So basically, we're looking at, if you're doing LES, you're delta plus is a factor of 10 larger in every dimension, roughly 8 to 10 larger in every dimension. So these are observations that we get, and the question is, can we fill the gap between these observations? I use them as constraints in my computation, but the other thing that the Navier-Stokes does is between the measurement, I have to satisfy the equations. So I try to find the flow field that reproduces this data and satisfies Navier-Stokes. So these two videos are a comparison of the true flow that generated those subsampled observations and my prediction of what the flow looks like. So you can compare them visually. Of course, we can quantify it. And we've recently developed criteria. What is the coarsest resolution you can have in space-time? And for me to be able to reproduce the turbulence accurately. And we have a theoretical criteria now, and we've tested it, and it works very well. Basically, in a nutshell, if Joe tells me he can resolve the Taylor, he can measure within the Taylor microscale, I can fill the gap. If you start just the observations that I showed you, if you just use any sort of interpolation of the observation, this is the truth to the left of what the vortical structures look like. If you just take the observations that I started from, you don't get any of the vortical structures. If you do the algorithm that we've done, where we do Navier-Stokes interpolation, as some of my colleagues like to call it, so you infuse these measurements in the simulations, this is the prediction that we got. We quantified the errors, but here, I think the pictures are somewhat compelling. The errors are less than a couple of % in the predictions of the velocity field. Filling in the gap, so now imagine if there's a region of the flow where we don't have information at all. So now I just basically deleted everything that was in the buffer layer and below, and we try to reproduce the flow below that. You can see statistically the computations latch onto the true flow. And if you look at the wall stresses that we predict, to the left, this is the streamline stress from the true like the reference calculation, and this is our prediction of the stress from our measurement-infused calculation. This is the streamline stress, this is the span-wide stress. So if there's interest in getting the stress and you cannot measure all the way to the wall, we can come in and try to help get an estimate of the stress that is hopefully spatial-temporally accurate. So just to recap, what I see our role would be to take the measurement that we have, whether they're statistical quantities and we use them to optimize our LES models, or whether they are spatiotemporal resolved data or of some resolution, spatiotemporal data, and we try to make the most of them in terms of expanding their domain of influence, or basically constraining our LES to reproduce the actual turbulent trajectories that are observed in the experiment, and to fill in gaps in the data, and hopefully, well, generally near the wall. And I reiterate the notion of optimal sensing. The optimal place to measure is the place that allows me to discover the rest of the flow as accurately as possible using the Navier-Stokes equations, as opposed to directly measure the quantity of interest. At least that's, I understand the timing that might not be feasible, but it's something to keep in mind. Thank you.